You ever have a hunch? That gut feeling that a new idea is just better than the old one? Of course you have. We all do. But in a world that runs on data, how do we get from that simple hunch to actual solid proof? Well, that's exactly what we're going to break down right now.
I mean, think about it. We are surrounded by claims all day long. This new drug is supposed to lower blood pressure. This new way of teaching boosts test scores. This new ad is going to increase sales. But the big question is always the same. Is the change we're seeing for real? Or is it just random noise?
The good news is there's a formal, really powerful process for answering that exact question. It's called hypothesis testing, and honestly, it's the bedrock of how we make smart decisions with data. It's how we turn our gut feelings into actual evidence.
So at its heart, this is what hypothesis testing is all about. We take a small, manageable sample, a handful of patients, or a single classroom of students, and we use a structured method to make a really educated, statistically sound conclusion about the entire population. It's the bridge that takes us from a small experiment to a big, powerful idea. All right, so to do this right, we need a rule book. I want you to think of yourself as a data detective. You've got a case, and you need to follow a very clear set of rules to figure out what's true without messing up. So let's walk through those rules. Rule number 1 is to establish your starting point. This is what we call the null hypothesis, or H0. It basically represents the status quo, the world where nothing has changed. It's the boring assumption that the new drug does nothing or the new teaching method makes zero difference. It's the default reality that we're trying to challenge. And this is where it gets interesting. The alternative hypothesis, or H1, that's your hunch. That's the exciting new theory. It's the claim that the drug does work or that the teaching method is better. Our whole mission as a data detective is to find enough evidence to throw out that boring old null hypothesis and embrace this exciting new alternative. This brings us to a really crucial idea in statistics. The null hypothesis always gets the benefit of the doubt. We have to assume it's true right from the start. Our job with our data is to gather enough evidence to prove it wrong. It's just like a courtroom. The null is innocent until proven guilty. But just like in a courtroom, we can make mistakes. A type 1 error is a false positive. This is when we reject the null hypothesis when it was actually true all along. That's like a wrongful conviction. On the flip side, a type 2 error is a false negative. We failed to reject the null when it was totally false. That's like letting the guilty party walk free. Balancing these two risks is absolutely key. So, how do we actually measure our evidence? Well, the star witness in our courtroom is the p-value. It answers a very specific question. If the null hypothesis of no effect is actually true, how likely is it that we'd see the results we got just by pure random chance? A tiny p-value, usually less than 0.05, means our result is really, really surprising. It's the statistical smoking gun. And here it is, the entire game plan laid out step by step. You start by stating your hypotheses and setting your evidence threshold. Then you go out, you collect your data, you calculate something called a test statistic, which is really just a number summarizing your sample, and you find its p-value. Based on that p-value, you make a decision. It's this structured, repeatable path that every single data detective follows. Okay, so we've got the rules, now we need the tools for the job. What if our pace is all about numbers? Things we can measure and average, like test scores or blood pressure. For that, we turn to a famous tool called the t-test. The simplest version is the one-sample t-test. This is when you have one group and you just want to compare its average to some known established number. Like, is this particular class of students taller on average than the national average? This test will give you the answer. But what if you have two totally separate groups? Let's say students from school A versus students from school B. Or maybe a group that got a new drug versus a group that got a placebo. For this, you're going to use the independent samples t-test. It's the perfect tool for comparing the averages of two distinct, unrelated groups. And finally, we have the paired samples t-test. Now, this one is perfect for all those before and after situations. You're measuring the same group of people twice, say their blood pressure before a new medication and then again after. This test is specifically designed to see if there was a real, significant change within that one group. So here's a quick recap of our t-test toolkit. Got one group versus a known value? That's a one-sample test. Two totally separate groups? Go for the independent samples test. And one group measure twice? That's a job for the paired samples test. See, each test is built for a specific kind of case file. This brings up a really important question, though. Not all data comes in nice, neat numerical averages. What if your data is about choices, like yes or no, or categories like Democrat, Republican, or Independent? For that kind of case, we need a totally different detective tool.
And that tool is the chi-square test. This is our absolute go-to when we're dealing with counts and categories, not things you can average. It helps us find relationships hidden in tables of data. So, what the chi-square test does is it asks if there's a significant link between two categorical things. For instance, is there a real relationship between someone's gender and their voting preference? It can also be used to see if what we observe in real life matches what we'd expect to see, like testing if a six-sided die is actually fair or if it's loaded. Okay, so we have our two main toolkits, t-tests for averages and chi-square for categories. The real art of being a data detective is just knowing which tool to pull out for which job. So let's put them side by side to make it super clear. This right here, this is your ultimate cheat sheet. When you're looking at the purpose, are you comparing means or are you testing for associations? And for the data type, is your data made of continuous numbers or is it sorted into categorical buckets? The answers to those questions will point you to the right test every single time. So let's just boil this all down to one crucial point. If you remember nothing else, please remember this. When your question is about comparing averages, like is this group's score higher than that group's score, your tool is the t-test. But if your question is about the relationship between categories, like is this preference linked to that demographic, you're reaching for the chi-square test. Averages versus categories. That's the key. And that's pretty much it. You now have the data detective's rulebook. So the next time you see a headline or an advertisement making some big claim, you'll be able to ask the right questions. Was it about averages or categories? And how did they really go about proving their hunch?